Now let us move on to the dual field strength tensor, and then we can write the Maxwell's equations in the covariant form. So let us define here a fourth rank antisymmetric tensor epsilon alpha beta gamma delta. So this is the property of this is the following. You have three choices, +1, -1, or 0. So +1 for any even permutations, such as alpha could be 0, beta could be 1, gamma 2, delta is 3. So if you have a even permutation, that is 1. Any odd permutation, it is -1. If you replace the, for example, if you write 0, 1, 2, 3, then if you replace one of them between 2 and 3 as a 3 or 2, that will be minus. If you replace once more, that will be positive again. And that is 0 if any two indices are equal. So this is called a pseudo tensor under the inversion. So actually it has the time and space components. If you reflect the space part to the -1, like a parity, if you see x, y, and z, if you reflect those things to the minuses, so the sign will be changed. So it is called the tensor epsilon alpha beta gamma delta is pseudo tensor under spatial inversion. So at the point, let us contract the two indices and convert this 4-rank tensor to the rank 2. So the definition is the following. F tilde alpha beta is the free indices of the tensor, is equal to 1/2 F delta gamma contracted with 4-rank tensor such that alpha beta will be free at the end and gamma and delta will be contracted. So basically if you sum up these 0, 1, 2, 3, 0, 1, 2, 3, you will have this and you will have a free second rank tensor with the components alpha beta. So the bottom line is the following. If you do this calculation, I will do only one term. You will obtain 0. So again, minus bx minus by minus bz bx by bz. Diagonals are 0 and this is Ez. It is a anti-symmetric matrix, so along the diagonal you have to reflect the signs and to put the appropriate reflection cells. So Ez goes to minus Ez and minus Ey reflect to the here is a plus Ey, and here you have Ex and here you have minus Ex. So this is called the dual field strength tensor. What is changed if you make a comparison between the field strength tensor and dual field strength tensor? What is changed? Look at this too. What is changed? For this, when indices up and down, E goes to minus E. But if you look at here and here, what is changed? E goes to B. B goes to minus E, I think. So the change between them is the following. E goes to B, E goes to B, B goes to minus E. Okay, the sign is changed. So this is the dual field strength tensor, and you see that the duality E and B are replaced. So with these tools, we can determine the Maxwell's equations. But before going to do, let me show you one component of alpha, F dual alpha beta. So let me show you one component, F0, 1, for example. So by the definition, that is equal to 1 over 2. Free indices 0, 1, and contracted indices is gamma delta, F gamma delta. So I want to calculate 0, 1. 0, 1 is minus Px. Okay. So if I put here 1, this will be 0. If I put here 2 and 3, that will be 0, 1, 2, 3. 0, 1, 2, 3, that will be 1. If I put 0, 3, 1, 3, 2, that will be minus 1. All other combinations contains what? 1 or zeros and so on. That will be all of them 0. So let us calculate this, for example. 1 over 2, 0, 1, 2, 3, that is 1. What is the gamma? 2. What is the delta? 3. So indice is down, and look at the where. This should be what? 2. This should be 3. What is the 2, 3 here? What is the 2, 3? 0, 1, 2, 0, 1, 2, 3. That is the cell minus Px. So minus Px. And x represents the x coordinate component, x component, sorry. And how about the 0, 1, 3, 2? So this is an odd permutation. The sign is negative. and there's a 1 over 2 here. So if you put 3, 2, this should be 3, 2. What is 3, 2? 3, 2, 0, 1, 2, 3, 0, 1, 2. Which one?
Plus bx.
0, 1, 2, yes, plus bx, plus bx. So that is plus bx. And altogether, this is equal to minus bx, 2 times of this, that will be minus bx. Is it correct? What is the 0, 1? 0, 1 is minus bx. Okay? So this is a simple calculation of the one component of the dual field strength tensor. Now, let us try to write the Maxwell's equations in covariant form. So we have now tools, field strength tensors, and the dual field strength tensor. So if you think about the f alpha beta, if you take the derivative with respect to the alpha, so these alphas will be contract, free index should be the beta, and that is equal to 4 pi over c j beta. So this represents the inhomogeneous Maxwell's equations. What are the inhomogeneous Maxwell's equations? Divergence of E is equal to charge density in Gaussian units 4 pi times that, and curl of B minus 1 over c del E over del T is equal to 4 pi over c times the current density. So these are the inhomogeneous Maxwell's equations, and we can test whether this covariant representation is satisfying these inhomogeneous Maxwell's equations. First of all, how many free indices you have? So how many free indices? Beta. Beta is what? 0, 1, 2, 3. 4 independent equations. How many equations here? One scalar and vectorial 3. So you have to equate the components. So you have 4 equations and 4 equations. So you have 1 and 3, 4 equation, and here you have 4 equation. So let us control to the result, one particular case. So one particular case, let us control the result. So if you write, for example, for beta equal to 0, what we have to write? Del alpha f alpha beta is equal to 0, 4 pi over c j0. What is j0? What is j0? If you say beta is equal to 0, this is j0. 0. C's will be cancelled. And here is a contraction or summation. So the open form of this is equal to del over del x0 f0, 0. The other part component del over del x1 f1, 0, del over del x2 f1, 2, 0, del over del x3 f3, 0 is equal to 4 pi rho. What is the f0, 0? f0, 0 is 0. What is F10? Ex. What is F20? Ey. And what is this? F30 is Ez. And how about the del over del alphas? Del over del x1, sorry, del over del alpha, yes, del over del x1 is del over del x, del over del x2, del over y, del over del x3, del over del z. So this is nothing but del over del x, ex, del over del y, ey, del over del z, ez is equal to 4 pi rho, and nothing but divergence of electric field is equal to 4 pi rho. Okay? So this is for beta equal to 0. If you do for beta equal to 1, what you are going to obtain? For beta equal to 1, J will be for beta equal to 1, J will be what? X component of the current density, and you will see that the X component of the curl of B minus X component over del X. Okay, so as the exercise, do the others by yourself. So this presentation is the covariant form of the inhomogeneous Maxwell's equations. How many equations? 4 independent equations. So inhomogeneous Maxwell's equations. And again, this presentation is the same in any inertial frame. Let's say prime. Okay, the form is the same if you go to different coordinate systems. So everywhere is the same. Every inertial coordinate system, you will get the same structure of the Maxwell's equations. So that's why it's called covariant. So as you guess, we left with the other 4 Maxwell's equations in components is a independent as a independent equations. What are these? Homogeneous Maxwell's equations. So for homogeneous Maxwell's equations, we have del dot B equal to 0, curl of E plus 1 over C del B over del T is equal to 0. No sources here. And again, we will come to this. This field strength tensor is constructed with the help of these two, because these two tells us that the magnetic field is equal to curl of E, this one, and the other one tells us that the electric field is equal to minus del vector potential over del T minus gradient of the scalar potential. Okay? Now, the covariant form of this is expressed simply in this equation. Del over del alpha, now F dual alpha beta. Okay. So here we use that the dual. How many independent equations here? 4 again. 3 and 1. So you have to contract this. Now let me show the one of them again for you. So let me show a different one, not the divergence term, the other one. Maybe this one. So keep this, calculate that the beta 1, for example, beta 1. So that alpha So unfortunately, there is not much place. So del alpha f tilde del f tilde del alpha f tilde alpha beta 1 have to be 0. And what is the open form of this? So I'll go and work there, so no place. So the contracted index is alpha, that is 0, 1, 2, 3. So the open form of this will be del over del x0 f tilde 0, 1 del over del x1 f tilde 1, 1 del over del x2 f tilde 2, 1 del over del x3 f tilde 3, 1. Did I do correctly? Yes. Alpha 0, 1, 2, 3. Now, there is a no mistake. Okay. What is the f tilde 0, 1? What is the f tilde 0, 1, the first term? 0, 1 minus bx. Minus bx. What is the del over del x0? That is del over ct. So that is, so take the minus outside, del over del t, del x0. What is 1, 1? 1, 1 is the diagonal term, 0. What is 2, 1? 0, 1, 2. 0, 1, 2. 0, 1. Minus what? Ez. Minus Ez. Minus Ez. What is del over del x2? Del over del x2. Del over del y. Did I write incorrectly? This is incorrect, I think. Del over del y. This should be Ez. This component, Ez. 2, 1 is the Ez, right? If tilde 2, 1. Ez. What is f tilde 3, 1? Ey. What is del over del x3? Del over del z. So you will obtain del over del z of Ey. Actually, what is this? What is this? Of curl, yes. So basically, we find that the x component of Faraday's equations if you do for the others, you will definitely find the exact result. So we have another equation that is the covariant form of the homogeneous Maxwell's equations. And this is the same in all frames. So as you see that we are building up the covariant form of the electrodynamics using the field strength tensor and dual field strength tensor. And what is left? The leftover is what? Maxwell's equations we have. we have the continuity and wave equations in covariant form. In the beginning, we started with the 4-dimensional Lorentz force. Can we write this in the covariant form? Yes, we can write. So in covariant form, dp alpha over d tau is mass times the proper time derivative of the forward velocity with respect to the d tau is q over c f alpha beta u beta. So this is equivalent to, this is the equivalent to dp0 over d tau q over c u dot e and dp over d tau q over c u0 e plus u cross b. So this is the covariant presentation of the 4-dimensional Lorentz force in terms of the field strength tensor. So the multiplication of the field strength tensor with the 4 velocity is the covariant form. Q and C are invariance, and this is the Maxwell field strength tensor, and this is the 4 velocity, and this structure is the same in all frames. So practically, if you want to calculate this dp 0 over d tau, and what is this in this presentation? So instead of free index alpha, put 0 and let it sum the other terms, q over c f0 beta u beta, beta is 0, 1, 2, 3. So in this is up, so I can use this. So that is equal to dp0 over d tau. So if this is up, this should be up again, sorry. So that is equal to q over c f0 0 u0 f0 1 u1 f0 2 u2 f0 3 u3. So f0 0 is 0, and what is the f0 1? f0 1 minus ex, 0 2 minus ey, 0 3 minus ez. What is u1? So that is covariant. So when the index is down, the vector space part will be negative. So basically u alpha, when the index is down, should be equal to what? u0 minus u. Therefore 0 1 is minus ex, u1 is x component with minus sign. So altogether you will obtain from here dp0 over d tau as q over c. So this will be minus ex, this is minus ux, and the others is the same property, that will be nothing but u dot e, the power. So basically the 4-dimensional Lorentz force in the covariant form expressed in this format. So we obtain the covariant forms of the all electrodynamics equations. So in the matter, what will be changed? If you want to write these equations in the matter, only affected terms will be the source terms. So this equation D will be electric field will be the electric displacement, and the B will be H. The source-free equations will not affect it. So in the matter, you can write the Maxwell's equation, the covariant form, in the following form. So F alpha beta is here has the components of E and B, but in matter we call, let's say, G alpha beta, that is nothing but electric displacement, and the H, and Maxwell's equations becomes to the following form: del over del alpha G alpha beta is equal to 4 pi over C J beta. Alpha is the contracting index, beta is the free index, and the other one will not affect it. So these are the Maxwell's equations in the matter. Now, I didn't show you that another representation of the Maxwell's equations, homogeneous Maxwell's equations, in terms of the F. So take this just a presentation. If you solve, that could be expressed in terms of not only F tilde, in terms of the F, the form is a little bit more complex. Del alpha F beta gamma plus del gamma F alpha beta plus del beta F gamma alpha is equal to 0. So this is another presentation of these homogeneous Maxwell's equations in terms of the field strength tensor. So I just show you to be familiar the presentation. So alpha, beta, and gamma are indices 0, 1, 2, 3. Now, the leftover term is the transformation of the electromagnetic fields. In one frame, you can have electric field only. Suppose that you are looking at the space from the reference frame of the charge. But if you have an observer, inertial observer moving somewhere else, you can observe both electric field and magnetic field. So we said that the Maxwell's equations are covariant, form is the covariant, and we have the Maxwell field strength tensor. And if we boost the Maxwell field strength tensor, if we look at with the different frame, how the fields will be changed. The form of the Maxwell field strength tensor doesn't change, but the elements change, and that causes the transformation of the electromagnetic field. So in general, let us remember that how we can transform the field strength tensor. So we have a F gamma delta. If we transform to the another frame, so okay, you have one frame K, in other frame K prime. You can write the Maxwell field strength tensor in one frame. You can write the Maxwell field strength tensor in the other frame. Equations doesn't change in the form, but the elements will be changed. So the electric field will be E prime x, magnetic field will be B prime. So electric field goes to the E prime, magnetic field goes to the B prime. The structure is the same, that's an anti-symmetric tensor, but the elements will be mixture. In the EX prime, in the K prime, EX prime could be expressed in terms of, for example, BY, BZ, and so on. So the fields will be mixed. The general transformation property is the following. So if we say that F gamma delta in the new frame, let's say K prime. So let's say here we have the E and B's, and here we are seeing that as a E primes and B primes, and that will be transformed as what? Del over del x. This will be contract with delta and left a free parameter, free index beta. Let us call this is a alpha beta. So these two indices will be contract and left a beta, and similarly for the gamma component of the field strength tensor will be transformed as del over del x gamma and left a free index alpha. So this is the transformation of the field strength tensor in the new frame. So this is generally expressed in the following format also. So people express, instead of writing this partial derivative, write in a lambda, and gamma contract goes to the beta. This term is contract, and delta is contract, goes to the beta is a free, and the other index is a free is alpha. Gamma is contract. So this contract and these two is contract and left a free index alpha. This is another presentation. They are equivalent. So all we have to know the transformation matrix, and as a tool for the transformation matrix we have boost matrix in one dimension. I haven't shown you the three-dimensional boost matrix. I will derive, or I write the derivation, put in the internet, but in one dimension is enough. So what is the one-dimensional boost matrix? What was the one-dimensional boost matrix? Do you remember? In one dimension, what we said that if we have a space and time, we can transform using the Lorentz transformation. So that was equal to what? A was equal to cosine hyperbolic psi minus sine hyperbolic psi 0, 0, and the other is minus sine hyperbolic psi cosine hyperbolic psi 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So this was representing the boost along the x direction. So basically that is equal to what? That is equal to we know that the cosine hyperbolics and sine hyperbolics, that is nothing but a boost along psi along x direction is equal to cosine hyperbolic psi was nothing but the gamma. The other was minus gamma beta 0, 0, and this is minus gamma beta gamma 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So I told you that if you use the 4 vectors, so tell me 4 vector here, space and time, for example. If you act this, you can find that the Lorentz transformation of the space and time. Another 4th vector, tell me what tools we know. For current density. If you act the 4 current density to do this, you will see that the new 4 current density in the one moving frame. For example, in the rest frame, if you don't have any charge density, you can have the charge density in the moving frame. Okay. So another 4 vector. Yes. Suppose there's a dipole, and you are sitting at the dipole, you are seeing a scalar potential. If the dipole is moving, and if you are rest, you will see a vector potential part also. How you can do this? In that case, you have the 4 potential here. If you boost it, and you can find that the 4 potential in the new frame. But the only thing here, this boost is designed to do along the x direction. Anything is moving, you call as a x. But here I discuss about the transformation of the vectors. But now I am discussing about the transformation of the tensor. If you want to transform the tensor, you have to apply this process. So these are the lambdas. For example, lambda 0, 1 corresponds to the what? Lambda 0, 1 are the elements of this boost matrix. But I am not going to do this. That is a nice way in the indices. I will study this just a matrix presentations. I will call this as a f prime. I will do this next time, f prime. And f prime is equal to boost matrix A transpose. So this is similar. Do you remember this kind of transformation in some mathematical courses? It's similar to the similarity transformation. So basically, this is the component-wise presentation of the transformation. But if you write this in the matrix form, this will be the transformation. So F will be our field strength tensor. A will be our boost matrix, and A transpose will be the transpose of the boost matrix, and the transpose of the boost matrix is the same, doesn't change. It is not complex. If you replace it, the rows and columns doesn't change. So then I will have a new field strength tensor, and I will see that all fields are mixed. Electric field and magnetic fields are mixed to each other, but the form of this tensor is the same as the tensor is here. It will be again antisymmetric second rank tensor. So next time I will study that the field transformation of the electromagnetic fields using the boost matrix in one dimension, and I'll study in terms of matrix presentation. Instead of working with the indices, I will do this calculation in the matrix presentation. We can see better what is going on. Index presentation is much more easy and fast, maybe 10 minutes I can drive. But we have to use some rules, and we don't see what is going on. But in this crude approach or raw approach, we can see that the elements of the field strength tensor one by one. So, okay. So our aim is the following. Our final aim is the following. Suppose there is a charge, and charge, we have the electric fields. if you have a coordinate system or at the top of the chart, you can see the electric fields. But if you have if the charge is moving some velocity, and if you are on the frame, you can see that the electric fields from the point of moving the charge is uniformly distributed, spherically outward. But if you are an observer at the rest, if this is moving, then you will see that both electric fields and magnetic fields, and the electric fields will not be spherically symmetric. Some components higher, some components is lower. So this tool enables us to calculate that the transformation of the electric and magnetic fields. Then next time I will start the dynamics of the relativistic charge particles and the electromagnetic fields itself.